So hello everyone. I'm Jeremy Ryan Balondo, and today I'm going to discuss about the Otto cycle. So, introduction first. The Otto cycle is invented by a German engineer in 1876 by a German engineer named Nikolaus August Otto. Built the first working four-stroke engine, and it is a stationary engine using coal-gas-air mixture for fuel. The cycle of the Otto engine is called the Otto cycle, and it is one of the most common thermodynamic cycles found in automobile engines. So, what is an Otto cycle? An Otto cycle is an idealized thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. It is the thermodynamic cycle most commonly found in automobile engines. So, the cars used it is the commonly used motor engine used in motor vehicles in today's um, car industries. So this is the cycle analysis for of the four-stroke gasoline engine or Otto cycle. So it is an air standard Otto cycle has four processes and is a four-stroke cycle with four piston movements, which are required to complete the processes. Otto cycle requires two complete crankshaft revolutions to complete the four strokes. So here is the PV and TS diagram of Otto cycle, which we can see here is here we have the the first process, which is the isentropic compression from here, which is um, constant. We have constant entropy. Then next is from 2 to 3, which is the constant volume heat addition. So the temperature rises, but the temperature rises, but the pressure remains the same from 2 to 3. 2 to 3. So that's it. Then 3 to 4 is the isentropic expansion. From isentropic is the entropy is constant. So we have here 3 to 4, the entropy is constant. However, the temperature varies and also the pressure and volume. So last part of the four-stroke cycle is the from 4 to 1, which is the constant volume heat rejection, which is constant volume. So the volume remains the same, but the pressure, temperature, and the entropy changes. So this is this is the this is the description for. So first, the suction or intake stroke. So the intake valve is open while the piston moves down and bring the air fuel mixture into the cylinder. Compression stroke. Both valves are closed, intake and exhaust valves, and the piston compresses air fuel mixture by moving upward. So next is the power stroke. Both valves are closed, and combustion occurs by spark ignition, forcing the piston to move downward. Then the exhaust stroke, the intake valve is closed and the exhaust valve is open, and the piston forces the products of combustion by moving upward. So here are the basic formulas for the Otto cycle. So for the heat added, we have Q is equals to mass times constant volume, at constant volume since from the heat addition occurs at from process 2 to 3. So we'll use the formula mCV from and the temperature differences between the temperatures from point 2 to point 3. So next is the heat rejected. So same principle. Since the out since the heat rejection goes from the process 4 to 1, so we'll use the temperature difference of 4 to 1, which is the temperature difference from point 4 to point 1. So QR shows MCV delta T from 4 to 1. So here is the total work done by the system, which is heat added minus heat rejected. And then the cycle efficiency is the work net over the heat added, or the heat added minus heat rejected over heat added. So it is the efficiency of the cycle. Here is another sample formula, and the we can use this to find the efficiency. It still gives the same results. Then the clearance volume, which is the volume from 3 to 2, since it is where the piston is compressed upwards, and then the remaining volume is the clearance volume, which is the volume from volume 3 to and volume 2. Then the compression ratio is the ratio between the volume where where the piston is down, and then with the volume when the piston is compressed and the cylinder is compressed. So here's another formula: 1 plus C, or clearance ratio, divided by clearance ratio. So to look for the clearance ratio, the C is V2 over Vd, which is the volume displaced. So the volume displaced is equals to the total volume of the cylinder minus the volume of the compressed cylinder, the clearance volume. So here it is, the formula. For specific heat ratio, since it is always the heat ratio for standard for air is always 1.4. So that's all, and thank you.